Well, Pat, we're finally getting together. We do a lot of testing, trying to figure out how to maximize our quality of our connection here. And I can't tell you how much I appreciate you.
Yeah,
But
no problem.
absolutely. Well, I also like learning from you. And specifically, you had written an article on single lambda. And I dip in and out of the optical world, generally related to whatever project I happen to be working on. And inevitably, because you've been, make sure I get this right. Tell me what I'll have you say it. What is your title and how long have you been doing it?
Okay, I'm a product manager at Cisco. I've been a product manager um, 7.5 years at this point.
Yeah.
Yeah,
You
actually almost 8.
starting
Yeah.
to get a feel for it? You starting to
Uh,
get comfortable
I'll
with the
never
group?
get there.
Get to
I'll
know
never
people?
get there, man.
Yeah. Do you feel like you know your office mates?
It's a lifelong journey.
Yeah.
Yeah.
No, it's interesting because I'm always fascinated by how we get to where we are on any given technology, because it always tells us a bit about how fast we can expect things to change, and then how things change versus when they're made available. It can differ greatly in terms of actually being rolled out in production, so to speak. But also, I just want to draw something else out here. You and I had a separate conversation about this, and I just want to bring it up because sometimes I know, I don't always tell people, but I've worked in marketing, but it's technical marketing for a long time. And you're very much, on a technical marketing type of role in product management. But I don't want to overlook the fact that you've got a very engineering heavy background. You've got, just give me the very brief 30-second version. You've got your PhD from MIT or PhD from
MIT.
MIT.
Yeah.
It is MIT. Okay. And then where was your undergrad?
MIT, but then I went over to USC, University of Southern California, for my master's.
Okay.
Then I went back to MIT for the PhD.
Yeah. And then
Which,
and what did
which
you
a lot
study?
of people thought I would never do, but I did.
Sure. Yeah, because you actually left school. I mean, you finished up, and then you were working, and then you decided to go back. That's not an easy turn once you've been out in the market, I would assume.
Yeah, it was a little bit different because the place that I worked at wasn't like any normal place you work at. It's Bell Labs, which is more like a university than
Another
commercial
pedigree.
environment.
Yeah, very learning focused. You guys
Definitely.
pushing the envelope of new revelations, so to speak.
Totally. Yeah.
Okay.
Incredibly smart people there. It's basically like being at a university.
That's so neat.
Pretty
I forgot
much,
about that
yeah.
pedigree too. That's a great one to bring up. But what's your PhD in, or how do you say it? What is your what do you
I mean, I
officially
was always
recognize?
in the Department of Electrical Engineering
Okay.
and Computer Science, but my focus has always been optics,
Okay.
basically like applied physics.
Okay. Okay. Well, that's perfect. Let's use that as a launch point then. So you wrote about single lambda, and I need a re-education when it comes to understanding where we are today and how we got here in terms of optical as a setup to why you're speaking of what can be done and where we're pushing the envelope, or the industry's pushing the envelope in single lambda. Does that make sense? If we start with the history first, maybe, and some terminology.
Yeah, I'm so glad you brought this up because it's just so fascinating how things develop over time and like technologies.
Yeah.
It's not always that predictable. I mean, yeah, you can generally see ahead by looking at what the researchers are doing, and you can pretty much figure out what's going to happen in the industry, maybe a few years in advance. But if you look at like 10 years in advance, it's really hard to predict. So it's really interesting to look back and see how things progressed.
Yeah, and I think sometimes I know, working from a Cisco perspective, because you actually interact a lot with customers in your role, and you have to understand how your customers are actually deploying things. And when I live in the pure marketing side, telling stories about what Cisco's, is what I've done for the last 20 years, wants to talk about, that always is stuff that we want customers to move towards, which may or may not be exactly where they are. So I'm just making that distinction because I think, where would you say customers are today in terms of optical technologies? What is good? What is bad? What's the best way to kind of understand the current state of optical?
Well, you have to divide the customers into different segments because there's a wide range. And, Cisco is a huge company, and Cisco has a whole bunch of different kinds of customers. And it ranges all the way from like the bleeding edge users like hyperscale, like, the Googles and Facebooks,
Yeah.
Microsoft, Amazon, that type of customer, all the way down to, the bank branch that just needs to connect their phones to something, right? So they can connect to their service provider. So there's a whole range of applications and types of networks that are used, and they all pretty much all use pluggable optics, which is the type of product that our group
It's
manages.
a good distinction because you educated me once before on the fact that there's optical in a generic sense in terms of a whole range of technologies. And Cisco has a lot of people working in areas that don't necessarily work with your group. Your group specifically focuses on optical transceivers, also
Right.
called pluggables, and a few other
Yeah.
nicknames that get
And
confusing. Yeah.
yeah, I don't know if this is a universal terminology, but this is the one that I try to stick to because it does get very confusing. But at Cisco, we have an optical group, and they work on optical transport systems. So that's a very high end, very high bandwidth, long distance,
Okay.
sometimes super long distance, even like submarine, like from coast to coast across the Pacific Ocean, that kind of thing.
Not something that
Um,
comes in a pluggable form factor, I would assume.
Not
See, these are
yet.
big boxes. Yeah,
Not
we're always working that way, right? Smaller, faster. Yeah.
But yeah,
Okay.
so far, no. Um, I mean, to some extent, it's getting there actually. But our
Wow.
group manages historically has been more Ethernet based,
Okay.
which is more like the datacom side of things.
Okay.
The optical side of things, that's more like that's it historically has been driven by like telecom.
Okay.
So service providers, big service providers, right? Um, the types of standards and protocols actually are a little bit different. I think the world is kind of converging on Ethernet as time goes on,
What is it
more and
that's
more.
not Ethernet that's still being used?
There's like I don't know if you remember something called Sonnet
Oh yeah.
back
Okay.
in
So
the
sonic
day.
ring
Yeah,
technology. Okay.
yeah, there could be Sonnet rings or just Sonnet. I'm by no means the expert, but there's some overhead you put in the headers of the packets
Okay.
to do things. And Sonnet was essentially so that you can have like very high bandwidth channels going through a long distance
Okay.
of
And I think it was
optical
pretty
fiber.
predictable, if I remember right, too, in terms of how it translated. But I might be thinking of something else.
Yeah, again, I
Well,
I
let's
don't know
focus
that
on
much about it,
let's
but
stay focused on the stuff that you're most concerned about, which is when we get into the optical transceivers. Um, these are significant little
yeah,
investments that are going to vary based on what distance someone needs to go, and also, of course, their
yeah,
ability to plug it in. I guess for it to fit. My
yeah. So pretty much whenever you buy like a Cisco switch or router or other companies' switches and routers, you generally don't plug the optical fiber straight into that box.
okay,
There's going to be a hole, of course, but you plug in a pluggable module into that hole, and then you plug the fiber into that pluggable module.
okay,
And like you said, because there are different distances that might be appropriate for that application, you're going to choose a different pluggable module because the cost range is very wide.
right, okay,
So if you're going only like 5 meters, you might plug in just even a copper cable. You might not even need fiber optics if you're only going a few meters. But sometimes you want to go like 40 kilometers.
right.
That's going to be a much different transceiver that you plug in compared to something where a situation where you need to go, 100 meters, for
Yeah, well,
instance.
it's a combination of distance and top and
The speed,
so
right?
the speed and your expectations about what you need to do might make the difference when you can't do it on copper at a certain distance with a certain speed, and that forces you into looking at optical for those
Hmm.
architectures. Okay, okay,
Yeah. So again, our group, we cover these little pluggable optics. They're like the size of maybe a pack of gum,
yeah,
maybe a big pack of gum. There's different standards of form factor
okay,
out there. There's SIP, QSIP. There's different
right.
flavors of both of those. So, um, yeah. So that's the type of product we manage, and like you said, depending on the distance, the speed, it can be 1 gig, or it could be 100 gig. We're looking at 400 gig this year, rolling out. That's kind of like the bleeding edge right now,
Okay,
400
okay,
gig.
okay,
I've personally been very involved with 100 gig, and like you said, the blog I think that you're referring to that I wrote is about a sort of a new generation of 100 gig optics. So
okay.
we've had 100 gig pluggable optics for years, but there's still a lot of life left in the use of 100 gig optics. But it's not like we're going to just be making the same stuff for years on end. We're constantly trying to improve on it. And in the case of the single lambda 100 gig optics, we're trying to simplify the structure of them so that we can make it more mass manufacturable, because that's really the key to the future.
Okay, because that allows you to scale and drop, and which cost goes down, which makes them more deployable. Market picks up.
Yeah,
drives cost down
goes
more.
Down.
Okay.
And then while we're doing this, there's other considerations. So yeah, definitely cost is like the big consideration. Mm-hmm. But while you're doing that, there are other decisions that you can make when you define like the standards around this new generation of optics that can make other things go easier, like how easy it is to upgrade your networks to 400 gig, for instance. That may not be immediately obvious to someone who hasn't really been involved at the level of detail that Cisco has. But that's something that we pay a lot of attention to.
Yeah. I mean, well, because today people are looking at how they do that. And with optical transceivers, you're not necessarily looking at backbone necessarily. You're right in the middle of everything.
It could be backbone, or it could be inside the data center. Okay. It could be like between spine and leaf layers in the data center. So spine and leaf, these are layers in like a very common data center architecture.
Okay, yeah, aggregation, core, distribution, that type of thing, right? Mm-hmm. In terms of where you may fit and what you need to accomplish. Well, let's in terms of, this is another confusing point, and so I don't mean to pull you off track here, but when I hear 400 gig, sometimes I think that sounds like a lot. Sometimes I think it doesn't sound like a lot, because it seems like we've heard those numbers, we've heard bigger numbers, and then of course we hear the numbers, but we don't always have the context in which to say, is that an accomplishment or is it not an accomplishment? But you're saying most people are able to do quite easily. Would you say 100 gig pluggable transceivers are relatively common and used with an SFP form factor today? What's kind of where's most of the market seem to be sitting and saying that's what I've got in my network?
So that's a really good point. When we I totally hear where you're coming from. Sometimes you'll see people or hear people say, and we can do a 1.5 terabyte, and you're wondering so is that good?
Yeah.
It totally depends on the context, right? So if you're talking about the total bandwidth of a switch or something, 1.5 terabyte might be pretty good.
Yeah, backplane switch.
If you're talking about like our product specifically, a single optical link, we're not anywhere near a terabyte yet.
Okay.
So 100 gig was state of the art, a few years ago. And it even depends on which form factor you're talking about. So it's hard to define like a single day when a new speed is introduced, because if you go back probably more than before I joined Cisco 7 years ago, or almost 8 years ago, 100 gig pluggable modules were already there. They were in a CFP form factor. CFP, which is kind of big. Okay. I think it's about the size of like an iPad mini or something in terms of the area.
Okay.
So, if you define it that way, then yeah, it's been around for a while. But today we have it in a QSFP28 form factor, which is, like I was saying, the size of like a pack of gum.
Okay.
And when it's in that small a form factor, you can get much more of these plugged into a single faceplate on a rack. And then it becomes more interesting for things like data center applications, especially for like the leaf spine architecture, because in that architecture, you really need tons and tons of connections. You need to connect every spine switch to every leaf switch.
Because they're forming a full mesh. And so that becomes almost the backplane of a scalable system. I think with a CLOS architecture. Yeah.
The leaf spine architecture became really important when the traffic patterns changed, because at one point, it wasn't so much about the traffic going from the server to the end user out, driving his car.
I think is north-south kind of how they normally term that?
Exactly. Okay. It became more east-west traffic, like server to server, because all of a sudden you had things like virtual servers, virtual LANs.
Yeah, or microservices that rely on things that could be in different locations or different parts of a... Okay. Yeah, I got you.
So then what leaf spine did was, instead of having 3 different layers in your hierarchy, you have just the 2. So, and you connect every single spine switch to every single leaf switch so that you can get from one server to any other server with a single hop. You go up to your leaf switch, you go up to one spine, and you go back down to another leaf switch. So it's just one hop. So that's really important for modern data centers
Reducing
today.
harm. Yeah. So, well, let me define something real quick. You said QSFP. That stands for quad something?
Quad small form factor.
Quad small form factor.
So it's a variant of the small form factor pluggable optic,
Which
like
is
SFP.
Okay.
SFP is 1 gig, SFP plus is 10 gig. We also have SFP 28, so that's 25 gig. So yeah, these are all the same size, but they're different speeds, but they're smaller than the quad SFP.
The quad actually is a different size, whereas SFP, those are versions of SFP, which, because that you're referring to the form factor of which that stick of gum or that transceiver plugs into a ready-made port that has to be built by the manufacturer in a switch or a router or some other type device.
Right.
Okay.
Right. So the manufacturer of the switch and router and the manufacturer of the pluggable optic, they both have to pay attention to the standard, which is called SFP or QSFP 28 or whatever standard you're aligning to. And so both the port, the hole that it plugs into, and the pluggable have to align to the standard.
Okay.
Both mechanically, electrically, optically for the high speed signal.
Okay. And just to make sure I don't miss this point, but we can bring back to go into the detail. But this is not IEEE standards that we might be familiar with. I believe these are called MSAs. Is that correct?
Yeah. Yeah. So for the mechanical form factor, there's an MSA called SFF.
Okay.
I think it stands for small form factor. Yeah. And they define the mechanicals. They also define the low speed electrical signals. Okay. So there's some low speed signals that do some management functions. The high speed signals, though, that actually is defined by the IEEE.
Oh, okay. Yeah. Man, everybody still has to work together.
That eventually turns into the optical signal, which IEEE also usually defines. Although recently there have been a lot of MSAs, not SFF, but other MSAs that have cropped up that will define the optical specification as well.
Okay. So when you go from an SFP, say, to an SFP plus, you got the same size, but the electrical setup, if you will, behind where that port makes a connection is ready to handle something over and above. The plus is more than the SFP, and then the SFP 28 you said was 25 gig?
25 gig.
Okay.
Yeah, so the way they do it, like if you have an SFP 25 gig or SFP 28 port, it's backward compatible. You can actually plug in a 10 gig SFP into that port.
Okay.
And it'll still work. You can't do it the other way around. You can't plug in a higher speed optic than the port can support.
That would be the dream. Yeah. Okay.
Yeah, that'd be nice.
And then I think when people using the SFP 28, which gives us 25 gig, that's not confusing to me at all. When you wanted to get to 100 gig, would you normally require 4 SFP 28 ports muxed together or bonded together in some fashion, or is that even a thing?
So the QSFP 28 is actually 4 SFP, it's the guts of 4 SFP 25s inside it.
Oh,
yeah.
So it's just hiding that complexity.
Basically, well, the complexity is, it's there, but it's hidden inside.
The user doesn't have to deal with it, or the operator. Yeah.
Yeah.
Okay. Oh, that's a good point.
So that's where the Q comes from. It stands for quad. That means there's 4 of them inside there.
Okay.
And in fact, even electrically, there's 4 lanes. So when you plug it into the port, inside that port, there's actually 4, 25 gig electrical channels there.
Okay.
So it's as if you've plugged in 4 separate 25 gig modules, but you're physically only plugging in one module that has 4 connectors.
Okay, let me ask you a question on that then. Does that mean, because this is a build up to where I think this goes with single lambda, but does that mean lambda, it refers to a wavelength of light, I believe, or a color. And those are relatively interchangeable in this conversation, I think, but stop me if I'm wrong. But then when you're talking about a QSFP doing 25 gig lanes, is that having to use 4 different colors to transport that? Okay. So you have a certain expectation of what kind of fiber you can do that on as well. So
what a great segue to single lambda.
I swear we didn't plan that. Yeah. Oh, you have a slide. Yeah. Hold on. Let me make sure I get the right thing. Does that work?
Yeah. Okay. So what you're describing is the left-hand green box there.
Okay.
I'm not sure if you can see my pointer here.
Try drawing if you don't mind. It'll make it messy, but I think it'll jump out further if you can. I don't know. Can we test this part?
Okay.
Make one of those ugly lines when you draw with a mouse.
I found the annotate button. And I'm drawing
There we go.
a terrible circle around.
I told you. Yeah, I love mouse drawing.
Yeah. So this is what you were describing, right?
Okay.
Okay. So here's the host port. This gray box is
Okay.
basically like the hole, or what's behind the hole. And these gray lines here are electrical traces, electrical connections
Okay.
to this lighter gray box, which is the pluggable module. So it's a QSB28.
Okay.
Right. It's my cartoon of a QSB28. And there's 4 signals going in this direction, 4 signals going in that direction. So it's 4 channels.
Okay.
Right. Electrically. Right. This is the interface between the host, like the switch or the router, and the pluggable optic.
Okay.
Okay. Inside the pluggable, you have the signals coming from the host, and it drives these transmitters. The transmitters are basically lasers with some circuitry like laser drivers. CDR stands for clock data recovery. That's to clean up the timing.
Okay.
And then we get to what you were talking about, the wavelengths. So in most of the QSP28 100 gig transceivers that are for like 10 kilometers and above, or even 2 kilometers and above, there's an optical mux inside. The optical mux is like a passive optical filter that takes the 4 different colors and it combines it into a single fiber. And that's what this pinkish arrow is.
Oh, okay.
So there's 4 signals and there's 4 beams of light of different colors, but then because they're different wavelengths, this device here can actually combine them into a single fiber. And then it goes on its way and goes off for like 10 kilometers or whatever. So there are transceivers that we refer to as LR4 or CWM4. Those refer to the optical standards.
Right.
Which means that you can get a module from any vendor, any company, even if it's not Cisco, that as long as they adhere to that optical specification, then you can mix and match on different sides of the fiber, any pair of transceivers, and they should still talk to each other because they both have aligned to the specification defined by that standard.
But you're not saying when those things get put together and they're on the outside the transceiver now on the optical part of the cable, say it's not a single lambda though at this point with that technology? Or?
Yeah. We haven't gotten to the single lambda yet.
Okay.
I'm still talking about how have things been.
What is it called that's doing that? So there's not 4 bands of light as I was kind of imagining it all the way across the cable. It's a 5th light or it's one combined channel?
These are 4 wavelengths of light.
There's still 4 wavelengths supported all the way across. Okay.
Yep.
Okay.
Yep, they go all the way through to the other end of the fiber, and it could be like 10 kilometers long, maybe even 40.
Okay.
And on the other side, you could have another one of the same things, except it would go into this side, the receiver port.
Okay.
The receiver fiber, and it would get demultiplexed, and it's just pretty much the same thing, but in reverse.
Okay.
The wavelengths get split up into these 4 different discrete receivers, and they go into the 4 different channels of the QSP28 port.
Okay.
So even if this were not a QSP28, if it were CFP LR4, it would still talk to a QSP28 LR4 on the other end because the optical specification was standardized.
You said QSFP LR28 or 28-LR?
QSP28 is the form factor.
Okay.
LR4 is an example of a IEEE defined optical specification.
Okay. I think LR is long reach?
I think so.
Okay.
Yeah.
Yeah, because they generally have these ranges between small, medium, and large or something like that, if I remember.
There's SR, short reach.
There we go.
Okay. I think I read somewhere SR doesn't actually stand for short reach, but it kind of sounds better.
Yeah.
LR, ER, I think is extended reach, and then ZR is... Yeah, I don't know what it stands for, but it's even longer.
Yeah. It's plaid. Okay.
Yeah. Okay. So that's how things are today for wavelengths.
Okay.
Now,
go back to the drawing.
We were talking earlier about like volume manufacturability.
Yeah.
Right. Now let's think about 10 gig SFP plus transceivers today.
Okay.
If you look at the total market of 10 gig LR transceivers, the industry is cranking them out at like a rate of like 10 million per year. Okay, so 10 million for us in the optics industry is a huge number.
Okay.
Now,
Sounds big.
if you make iPhone components, that may be a drop in the bucket.
Right.
But for the optical industry, that's a very large number. So it's a number where if you're at that volume, you've had enough time and you've had enough iterations to work out a lot of the kinks in the process,
It's mature.
optimize the process, the assembly process, testing, everything is optimized, and maybe there's even an industry infrastructure built around that particular, say like the SP Plus transceiver, so that all that stuff is made even more efficient because other companies might develop new testing equipment, they might develop jigs. This is something that happens in any industry. Right. As it becomes more mature, things get more efficient.
And that's QSFP, you're saying? That's what you're saying is in the millions?
That was SFP
or that was SFP
plus,
that's in the millions?
10 gig
Okay.
SFP plus, right? So remember, 10 gig came out, I wasn't even in the industry at the time. I think probably early 2000s, mid 2000s maybe.
Okay. It takes a while to get mature. Yeah.
Well, I think it matured fairly fast, but it's still going strong today. So it's definitely had a very long lifetime.
Okay.
Still going strong today. But I think basically with 100 gig optics, if we want to get down to a cost level where 10 gig optics is today, we need to be able to get the simplicity of the structure inside at the same level of complexity. So right now, it's not. Right now, we have 4 channels inside. So we have 4 of everything.
Yeah.
And then you have this mux and demux. If you look at an SFP 28 or SFP Plus module, the diagram that I would draw would look something very similar to what's on the right-hand side over here. Just one laser, one receiver, some simple circuitry, and then just connects directly into the host.
So that's the goal. That's what you want to get to.
That's the goal. Yeah, this is the end goal. Now, what I drew here is not SFP 28. It's something that doesn't exist yet.
Okay.
It's probably going to be called SFP 112, but there are people working on it.
Okay.
The limitation right now is that there isn't even a standard yet on the host side that defines what this electrical channel would look like.
Okay.
So, when that starts to come out, then we can talk about having a pluggable module that will just plug directly into that. And you can have a very simple 10 gig SFP plus like module.
Okay.
That's simple to manufacture.
Okay.
So that's the vision.
Okay.
Now, until we have that, there's still, so the point of this 100 gig Lambda, like the blog, was to say that, hey, even though we're not at this point yet, that doesn't mean we have to wait for this to come out in order to define the optical standards.
Okay, explain that further.
So the optical specification is something that defines just the optical side. Whatever happens inside here is up to the manufacturer. As long as you get the optical performance aligned with the specification, we don't care what's done inside here.
Well, that's what I was confused about, because I've seen you do demonstrations highlighting different areas where Cisco has been developing things in a certain direction. And so what you're saying is that's not something that's out yet, but that's Cisco working toward increasing capabilities on the optical side. Yeah.
So in Cisco optics, what we like to do is say, look, we adhere to all the standards, but we can do even better.
Yeah.
So we're constantly trying to come up with ways to make products that are solving problems for our customers that the standards may not be in a position to, or it may not have existed at the time that the standard was defined. So I think that's what you're referring to, and I think I might have another slide on that.
Okay, yeah, bring it up.
But let me finish the point of this slide.
Okay,
is really it's about this.
Okay.
So today so this is where we've been at for years. This is where we want to go, hopefully in a couple of years. But this is where we are today.
Okay, so from left to right, you're really talking about a progression. Okay.
Yeah, it's like, consider this a timeline from left to right.
Okay.
So where we are today is that we actually have a QSFP28 module that adheres to this optical specification. It's a single lambda 100 gig optical specification. It's just one laser, not four over here, but just one like over here. The difference is that because there's four channels here, you need some chip inside, an ASIC, that does that conversion from four channels of 25 gig to convert it into a single channel of 100 gig.
Okay.
So that you can modulate this laser.
And so when you say this is what's available now, you mean the technology is shipping, everything is there, it's in an acceptable form factor? Okay. So customers are buying that and using that. Okay.
Yeah. Yeah. We actually have a QSB28 module that is basically this, and it's called FR. I don't know what the F stands for. I'm sure it stands for something. It's a 2 kilometer reach optical standard. There was an MSA that defined the FR specification.
Okay.
IEEE is working on a very similar one. I think they're calling it FR1. So it's standardized. It's going to be standardized by IEEE. So yeah, it's 2 kilometers. And I think what you were referring to was the fact that our technology that to implement this can do much better than can go much farther than 2 kilometers.
Okay.
Because we've invested a lot in silicon photonics over the years. And we have a very nice silicon photonics modulator that can modulate very cleanly so that when you propagate through the fiber,
less loss.
It's not so much about loss. So now we're getting into a little bit of the physics.
Don't let me drag you into that, but yeah. I should quit guessing and just let you finish your sentence.
It's really interesting, actually. It's the kind of stuff I actually studied a lot for years.
Well, then go get your geek on.
So,
yeah.
All right. Thanks. So if you, there are different ways you can modulate a laser. One way is just to turn the current on and off. Okay. So it's a semiconductor laser. Basically, you run current through the semiconductor. I'll leave out a lot of the details, but basically the laser light comes out.
Okay. It sounds very binary. Okay. On or off, 1 or 0.
It is. Okay. Yeah. And it's what's used for NRZ.
Okay.
Sorry. I jumped ahead.
That's right. NRZ has a compression. I think is one of the compression things used, maybe, or is it more than compression?
It's a modulation format. It basically refers to it's one of the binary modulation formats. Okay. The other one is RZ, return to 0.
Okay.
NRZ just means when you get to a 1, you don't automatically go back down to 0. You just wait until you actually have another data 0 before you.
It's not assumptive. Okay. Non-return to 0. Yeah. Okay. NRZ. Yeah. Okay.
Yeah. There was a Boston album called Return to 0. I was going to say NRZ, but it's Return to 0. Do you know the band Boston?
Oh yeah. No, it's
the guy Tom Scholz went to MIT.
So you think it was a legit reference? It wasn't just a here's 3 common letters that overlap.
Yeah, he's got credit. Yeah.
Oh, okay. No, I did not know that part at all.
He knew exactly what he was doing.
Yeah. Rock career. Okay.
Yeah.
More than a feeling. So, yeah. Okay.
Exactly. Yeah. Another side note, this single lambda 100 gig specification actually uses PAM4.
Okay.
It's not NRZ. It's actually 4 levels instead of just 2.
Okay.
And through PAM4, you can actually transmit twice the data using basically the same types of components that you would get.
Okay.
If you're using NRZ.
Okay.
So that's one of the things that the industry had to pull out of its bag of tricks in order to get this to happen.
Yeah.
Yeah.
Which means generally the tighter you're going, the more error correction and different things like this that you have as part of it, which can affect throughput, right?
Okay.
Or am I pulling you out of your pattern?
Okay, so now you're talking about all these. So there were a whole lot of. So I glossed over a lot. Okay. I said, hey, it's a 100 gig single lambda.
Yeah.
Easy, right?
Sure.
No. There's a lot of things that people had to do to get that to happen. PAM4 was one of them. Okay. You just touched on another one, error correction. There's forward error correction in the single lambda 100 gig standard. So basically, if you were to do the PAM4 modulation, what happens is, let me see if I have a slide on that.
Okay. I'll pull it off the slide for a second to, you can play around. It's not going to be broadcast for the moment. Okay. Yeah, you keep looking while I rip. Oh, there we go.
I have
okay.
It. Here it is. Okay.
Oh, that's good. Okay.
Okay, so this is NRZ. This is what I was saying. Like 0 is no light. A 1 is you got light. And it's
Okay.
pretty much light as you can put out. If you're at a 1 and the next bit is also a 1, you don't go back down to 0 before the next pulse period.
Okay.
Okay, so that's NRZ.
It stays at whatever the last bit of information came across is where it stays.
Exactly. So
Okay.
vice versa, when you're at 0, you don't make any transition.
Okay, that makes sense. Okay, I never did know what that meant. All right.
So that's non-return to 0. Return to 0 would look like this, but you would see like a dip here. You would see a dip right here because it would go down to 0 and then go back up to 1. That would be return to 0.
Can you explain? It's obviously we're looking at a picture here, but what is it that we're seeing? Is it looks like it reminds me of like looking at waveforms or something. Yeah. So what are these pictures?
So this is called an eye diagram. This is like a screenshot from the oscilloscope. And what the oscilloscope is doing is it's taking like a whole bunch of data, and it's overlaying like a single, I don't know, a single, this here is like 1 pulse period.
Okay.
So it looks like a 1 plus a half here plus a half here. So a total of 2 pulse periods.
Okay.
And it's overlaying all these transitions that are happening through some randomly generated data stream.
Okay.
So what you see is you're seeing like the average of all these. You're talking about like thousands, maybe hundreds of thousands of transitions, just kind of averaged out. So it's a way of looking at the quality of your modulation.
Okay.
So you get to see like this here would be like one of these where it doesn't actually change.
Mm-hmm.
This here would be like this one here, where you have an up transition. I know my drawing is terrible.
No, it's not your fault. It's the tools we have to use sometimes. Yeah. I think your drawing may be horrible.
Yeah, it's pretty bad. And so what you look for when you look at these is the eye. So you can see this kind of the shape of an eye.
And what makes a good eye?
You don't want to see any of this orange or white or red stuff inside
you want to clean.
the eye.
Okay.
Because if you see stuff there, that means that your pulse probably looked like this.
Oops. Yeah.
And my drawing in this case would actually be pretty good, because if it looks terrible like my drawing, that means the modulation is awful.
Okay. These are similar concepts to wireless. You know, you're interpreting.
Yeah.
You have to interpret what's being done, and how clean that can be done will make a difference in how many errors are introduced and what kind of throughput you actually get. Okay.
Exactly. Yeah. It's totally analogous.
Okay.
Okay. So that's NRZ.
Okay.
PAM4, instead of 2 levels, you have 4.
Okay.
Right. So there's 0, there's 1, here's another one, and then here's another one.
Which means your eye gets a lot smaller.
Exactly. And that was my point about this that you brought up, the forward error correction. So you're right. The eyes here, they're smaller than the ones in the NRZ, right?
Right.
And that means that the same amount of noise here. So you know, this line ideally would be like infinitely skinny, but it's not. It has some width to it, right?
Right.
From the top to the bottom.
Okay.
And
that's again, potential data that could be there if it could be thinner. Yeah.
Yeah. You don't want any noise spike to make it look so. If it's up here, it's a high level. You don't want a noise spike to make it so low that it gets interpreted as low, because that's a bit error, right?
Okay.
So noise is going to do that for you, but the noise here is pretty low, so most of the time it's not going to happen. You can see that in the eye diagram.
Okay.
But take that same amount of noise and apply it here. The same amount of noise is more likely to pass the threshold, the decision threshold, because look, the decision threshold is this much higher. For NRZ, the decision threshold would be like somewhere in the middle, but now you have 4 levels.
Okay.
So now you have a decision threshold that's way up here. So the same amount of noise is more problematic than it was in the NRZ situation.
Okay, that's what I was looking to hear, because so because I had studied wireless more heavily in the recent past, just the whole notion of is we have increased modulation that allows marketing to put things on your wireless advertising that say we're getting this kind of throughput and this kind of stuff. But the environment in wireless is much less controlled than fiber. And so you're dealing with a lot more environmental conditions. And so generally you find out that, well, you're only going to get that if you happen to be standing next to the transmitter. You have to have line of sight almost, and be very,
Right.
Virtually cabled almost. And so that type of thing has to be accommodated here. So as the envelope gets pushed, is what you're saying in here, they measure this stuff and they say, well, how far can we get with a reasonable amount of error correction, I guess, too, that has to be factored into that, because that's going to make a difference.
Okay, so let's think about the thought process of incorporating PAM4 and the consequence. So we go to PAM4 because we can get twice the data through, right?
Mm-hmm.
But at the same time, it's like, yeah, but now the component has to be really good in terms of noise performance. But that means it's going to be really expensive too, right? And we don't want that.
Okay.
So what can we do?
It's a balancing act. All right.
We can use forward error correction. Forward error correction can correct for a lot of these errors as a result of noise.
Okay.
And especially if the noise is well understood, forward error correction can be extremely effective.
So it's like throwing math at the problem. I mean, because you're filtering
an
to a
algorithm.
Yeah,
it's an algorithm
yeah.
specifically. Yeah, throwing math at it, specifically an algorithm.
Okay.
And it can work really well. So you can go from a bit error rate of, somewhere around 10 to the minus 5 or so.
Mm-hmm.
So that's like 1 in 100,000 to 10 to the minus 12. So 1 in a trillion.
Okay. So there's
because 1 in a trillion is where we like to sit at for Ethernet.
Really? Okay.
So historically, bit error rates for everything that we've been doing in Ethernet has been around 10 to the minus 12, 1 in a trillion. That's just how it's been.
Okay.
So now we introduce this PAM4 thing, and if you say, yeah, but bit error rates, 7 orders of magnitude worse, then it's like, no, we don't want that.
Yeah.
Right. We were happy with 10 to minus 12.
Okay.
So, forward error correction basically fixes that.
Probably to a certain extent. You can only throw so much at it because there's going to be a hit somewhere, a price
only
to
a certain extent. So let's say the noise was so bad that it brought it up to 10 to the minus, 3. Well, then the forward error correction is not going to bring it down to 10 to the minus 12.
Okay, we're out of the range.
Because it's been designed for a certain range and gives you a certain benefit.
Okay, so how does all this come back around? You're saying PAM4, is PAM4 used much today? You're saying it is within Cisco.
It is for this new single lambda 100 gig standard. So the standard itself that defines what the light modulation should be here requires forward error correction. So it requires PAM4. It requires forward error correction. And that forward error correction is actually, let me get my annotation thing here.
And those are things that can happen in the ASIC, I would assume.
It happens in this product. It happens in here.
Okay, yeah. The way Cisco does it. Okay.
Well, yeah. Now, these hosts, behind the host, there's the ASIC that drives the port.
Okay.
They can actually do forward error correction as well.
So that's a different ASIC. It's the one.
It's a different ASIC.
You're talking about ASIC in the switch or an ASIC in the router.
Sits in the switch, not inside the pluggable module. Yeah. So imagine there's another one of these green boxes, but to the left of this gray.
We love our ASICs. Yep. Yeah.
And so even in this situation over here, we've been using forward error correction. The thing is, the forward error correction that sits on the host, it's a different algorithm.
Okay.
LR4, which I mentioned before, does not use forward error correction, but some of the newer standards like CWDM4, for instance, that's not IEEE, it's actually an MSA, but it's very common.
Coarse wave division multiplexing?
Coarse wavelength division multiplexing, 4 channels.
Okay.
And it actually also requires forward error correction, which is built into the host itself.
Okay.
The thing is, for this to work, for the single lambda, we needed a stronger algorithm that doesn't exist on most of the 100 gig host platforms. So it had to be built into here itself.
So it's sitting on the transceiver.
Into the transceiver module itself.
Which you still had to keep to a pretty small form factor. Yeah.
Yeah. I mean, yeah. QSP28, even though it's bigger than SFP, it's still pretty small.
Yeah.
But so then the question is like, well, what are we going to do in a few years when we have this out? Well, that forward error correction has to be built into these new ports, SFP 112, that don't exist yet.
Okay.
But it has to be built into the to the host. And also the PAM4 modulation has to be done in here. So this signal here would be PAM4 modulation.
Oh, okay.
Right.
So
if you look over here, this signal here is NRZ. Similarly, this is NRZ because these are the same standard. And then this ASIC converts it into PAM4 over here. So that when it comes out here, it's PAM4.
So you're kind of shifting back where you do that demodulation, or where the modulation has to change. You're shifting where it has to happen off of the optical transceiver and into the host itself.
Exactly. Well, we have to offload that processing away from the pluggable, like it is in the QSP28 here. You offload it into the host if you want to have this lower cost, easier to manufacture 100 gig optic.
So let me ask you a dumb question on this one then, because this is where I get confused then. If all you're doing is pushing off the complexity into the host itself, you're just moving the not saying there's not a benefit, but doesn't that just mean that the complexity or the cost for that complexity is going to be borne into the cost of that host as opposed to the transceiver? What is the benefit to a customer if we assume I don't know. What's the general question? What's the benefit?
Hey, you're just moving the pieces around. You're not getting rid of anything.
Yeah.
That's what you're saying. Right?
Yeah, I think so.
I think on the host ASIC, the host ASIC is can do things much more efficiently than this little ASIC that's built specially just for
that makes sense then.
Pluggable module, right? Also, the host ASIC, they generally have much. They're bigger pieces of silicon. They're bigger pieces of technology because they do all kinds of things. I mean, the host port is just one little aspect of the overall design. It's doing all the switching and routing, right?
Right. So
that's its main function.
Okay.
And so they're going to use all the latest technology, like the fabrication technology, for that.
Yep. Okay.
So for them, it's kind of like, hey, we'll just add in this PAM4 modulation and forward error correction. It's really not that big a deal. For the transceiver module vendor to say, hey, I need an ASIC that does this and this and this that I can fit inside my module. That's
a whole different cost element associated with that, I would imagine.
It's kind of a big deal.
Yeah. Okay, that makes sense. Okay, they've got more real estate to play with.
Yeah.
I know Cisco itself is constantly pushing on the ASIC development to do more on the backplane and everything else. I mean, it's not that big a deal to add another role for that particular port because it's doing similar things for other ports. Okay.
And you want to take out processing functionality from the pluggable module because it just consumes power, and so much of like the thermals these days is based on cooling the optics now.
No, that becomes a limiting factor, in other words.
Yeah.
Okay.
Yeah. So you really want to minimize how much power your pluggable optics draws.
I think you showed, not to jump too far off here, but you showed some power dissipation features of something Cisco's working on, I thought, at one of the Cisco Lives, or maybe it was one of the optical shows. Does that sound familiar?
Oh yeah, I think you might be thinking of my colleague Ray Nearing.
Yeah, it was something you did with him.
Demonstrated the 400 gig QSP-DD form factor.
Okay.
Which can dissipate. We demonstrated like 21 watts. Yeah.
Okay. Yeah, that's not, and that doesn't have anything to do with what we're talking about here, because that's getting into another set. Okay.
I mean, it's related, but it's a different topic.
Okay.
But definitely related though.
So what's the right way to kind of bring this conversation around to something that we can take away? Because we see the direction going into single lambda, and it sounds like there's things that we have to develop along the way, so this is Cisco usual, because it happens, I've seen it in a lot of other areas too, moving faster because customers need this and can move faster than the standards bodies. At the same time, Cisco participates in these standards bodies, so I imagine some of these things do end up becomes a compelling way to guide the standard as well when you've got people that have put in the development time.
Yeah, that's a great question. So all this stuff is kind of like this is like my world.
Yeah.
And I think it's a fair question for someone like someone who deploys networks for a living to say, why should I care?
Yeah.
Right. That's Pat's world. Let him worry about that.
Yeah.
Why should I care?
Pat's crazy.
So the the end result of this, the net result of all this is that if you so I mentioned we have a QSP28 based single lambda 100 gig optic, right?
Okay.
And I also mentioned that, it's not the ideal that we're driving toward in the future. So the question is, so why should I bother with the thing that you have today? The reason is that if you invest in that technology today, then there's this built-in forward compatibility. Forward compatibility meaning like, okay, let's say you buy a bunch of, okay, there aren't any SAP 112 based hosts today.
Okay.
But let's say you want to upgrade to 100 gig today. Your only choice pretty much is QSP 28. So you do that. If you plug in this this FR single lambda 100 gig optic, you might be worried like, oh, you know, when the new thing comes out, I don't want this to be obsolete.
Right.
Well, it won't be, because even though the QSP 28 4-channel, 4 by 25 gig channel electrical interface might be phased out in the future, the optical standard that it adheres to is the same as what's going to be what the this next generation SAP 112 optic will support. So you could actually take your QSP 28 based optics that you get today, say the FR optic, and say 3 years from now you get some newfangled SAP 112 FR optics. You can still connect them together via fiber.
Okay.
They'll still talk to each other. So you don't have to worry about wasting the investment that you make today.
Yeah. Yeah, that's an interesting point, because there's such a cascade of things that have to work together. And when you talk about a network refresh, perhaps, which is a huge investment for most customers, you're talking about a cost of not only upgrading your gear, the host, as you've been referring to it, switches and routers, but then how they connect over optical, and can they use the previous optical transceivers or not, or are they going to have to invest in those? And can they use the fiber that they have in the ground? Because I imagine that's a limiting factor too, knowing their distance and then knowing what type of fiber. Is it multi-mode, single mode?
Yeah,
I think is some of the options.
And when a lot of people upgrade, they don't want to just like, they have switches and routers at different locations, whether it's within the same room in a data center or different sites, like different buildings.
Right.
It's really impractical to say, okay, I'm going to upgrade my network, shut everything down.
Yeah, no.
It will be all down. We'll be blacked out for like, a couple of weeks or however long it takes. No, what you'd really like to do is say, okay, we're going to take this one site. We've got the rest of the network to kind of cover. So, we'll be impacted a little bit, but this one site will be down for a little bit. Upgrade that and bring it back up, and then we'll be back up to where we were before.
Yeah.
That's what you really want. And so if you have these QSP 28 based optics around this year, then in 3 years you can take one of those sites and say, hey, I'm going to replace it with the new optics. That means that once you do that swap in, you can turn it back on and you'll be like functionally back to the same point you were at before you did the upgrade. And then when you upgrade another site, then everything will be back. It's basically just you're incrementing, you're upgrading one site at a time. Okay. And it's even better than that, because what we've been talking so far is 100 gig.
Right.
But what I just said applies to 400 gig as well. So this single lambda 100 gig optic can actually interoperate with 400 gig optics.
Okay. So
Right?
So
that's
lots of investment
another added
protection.
benefit. Yeah. Okay. So let's say okay, let me see if I can
go ahead and look it
find another slide. Okay, found it.
All right.
Okay, so let's go back to the scenario I was just saying. Let's say you bought a whole bunch of these QSP 28 based FR modules for your QSP 2800 gig switches or routers. And again, these are single lambda 100 gig. And let's say you decide on the left-hand side, you're going to upgrade it to 400 gig. All right, so you buy like, the Cisco 8000 series router, for example. You get something that's called a QSFP-DD DR4. I won't get into the details, but it's a 400 gig optic. It's another flavor of QSFP called double density, QSFP-DD. It supports 400 gig, but it's basically 4 channels of 100 gig on the optical side. So you can actually get a breakout fiber patch cord that has 4 pairs of these fibers, each of which will plug into individual 100 gig optics.
Okay.
So basically, again, you don't have to take down the whole network. You just take one site, you upgrade it to 400 gig, you turn it back on, and you can still have your connections to the existing 100 gig switches that you had before.
Yeah.
And this way, number one, you're not wasting any bandwidth. You're still using the full 400 gig of this 400 gig port.
Okay. Okay.
Because in theory, you could actually plug in a QSP28 optic into the 400 gig port.
Really?
You would just be wasting 75% of the bandwidth of that port. It would work.
But if you needed that to limp along to the next upgrade or something, maybe that's an option.
Yeah, you could do that.
Or if you're sparing parts, I would think these things kind of come up too. It becomes an emergency situation.
If you had one already and you just needed something, you could plug it in and it'll work. And then then when you get around to upgrading the other site, you replace this with your 400 gig switch and optics, and then this link becomes 400 gig per per link.
Okay. Wow. Okay.
So that's the other tie.
You say what's the status of QSFP DD DR4 today?
Yeah, we have some products released already, and some are coming out, I think, in a matter of weeks.
Okay. So I believe this is part of the 5th generation line cards are supporting this, I think, on the ASRs.
ASR 9K is going to support it. 8000 series already supports it.
Okay, that's the new one.
We have Nexus switches that support it.
So that's your path.
Yeah, you should bring Ray onto your show. I'm sure he can tell you all about this.
Yeah, it's funny how often his names come up and how often I've studied, based on your recommendations, I've studied his knowledge when he's sharing it as well, and I will have to get him on. But well, Pat, I feel the need to draw this to a close. Is there anything else that you want to make sure you get a chance to say that I'm cutting you off now from?
No, I think we covered a lot. I think you asked some really good questions.
In a good way. In a good way. This is exactly what I was hoping for. Now, how much I retain, it's a different matter, but that's why we record these things, so we can share them as well. But Pat, as always, I appreciate your time, appreciate everything that you do. I know all this stuff. You've got stuff on the web. You encourage people to follow you on your blog. I'll put a link to that in our show notes as well. Is there any other places anyone should be following you or looking out for you? Is that the best place?
I'll give you some links that you can post.
All right.
Yeah. One of them's not active yet, but
you got something coming. Excellent. Okay.
Basically optics.cisco.com.
Okay, perfect. I like easy to remember.
I don't think there's anything there yet, but we've been working on something.
It's nice when you get something in front of the Cisco.com domain. Yeah.
Yeah.
Usually they force you on the other side of it. But well, cool. Well, Pat, thank you so much. As always, I'm learning a ton.
Thank you so much.
And I'm going to come back to you with questions, and anybody that raises questions to me, I'm going to come right
back to you.
Okay, man. We'll take it easy.
Thanks. You too.